So, Geraint, we're still here in Croatia on the island of Hvar. We're at the John Bell Institute for the Foundations of Physics, trying to think about entropy. But today, we want to get you talking, and we want to talk about something which comes up an awful lot in the press, actually. They keep talking about Earth-like planets, and we want to go broader than that. So we want to know about what sort of planets can there actually be? We see a bit of a variety in the solar system, but once we get out and look into the universe, what sort of planets are out there?
Look, this is something I've been giving a lot of thought to recently. I don't work in planetary science, but I've been thinking about planetary environments because I've been thinking about life in the universe. One thing to remember is when you watch science fiction, there's a very limited number of kinds of planets people tend to go to.
Yeah.
Right? You pick a movie, right? Things like Star Trek, boldly go, blah, blah, blah. They get there and the gravity is gravity-ish, the temperatures are Earth-ish,
right.
All that kind of thing. Even
famously, every planet in Doctor Who looks an awful lot like a quarry in Wales.
It does, which is amazing.
Yeah.
And then even, you move into other kinds of science fiction, Alien, right?
Yeah.
So, there's the Alien movies have now spanned several movies into Prometheus, etc. Every planet they go to, maybe the weather's a bit rough in places, maybe they can't breathe the atmosphere, but it's still very Earth-like conditions, rocky surface, all this kind of stuff. And I think Interstellar tried. They did have their planet close to the black hole.
Yeah.
But the planet itself was a water world, so it had a watery surface. It was in a strong gravitational field, so there were huge tides, but still when they were plonking around on the surface,
you just run around.
Very Earth-like. So let's just sort of think about planets and the stars they're around.
Okay.
So let's just go to, you already mentioned the solar system. We have a variety in the solar system.
Yep.
Some rocky planets in the inner solar system.
Inner solar.
Gas planets in the outer solar system, right? The rocky planets, of course, we have this region called the habitable zone, where, twiddle, you have liquid water on the surface.
Yep.
And that's where the Earth roughly sits. But the other planets, they can be similar and different in lots of ways, right? You look at Venus, very similar to Earth in size and mass and surface gravity. Ridiculously different kind of atmosphere, very thick, very rich in carbon dioxide. Very, very massive greenhouse effect, very hot. So lead melts on the surface.
Yeah.
Mars, much smaller than Earth, not enough gravity to hold on to much of its atmosphere. It's lost a lot of atmosphere. Doesn't have a molten core, doesn't have a strong magnetic field, etc. Surface of Mars, exceedingly dry, very tenuous atmosphere. Mercury, the other rocky planet, which is a lot like the Moon, and we already know the Moon is not a place that you want to live. But Mercury has this issue, of course, is that the near side facing the sun, hot enough to melt various metals on the surface. Far side is pretty cold because Mercury rotates relatively slowly compared to its orbit, so it's a bit like a slow cooker.
So it's basically one side always points towards the sun.
Not quite. It's almost locked in that sort of rotation, but not quite. Okay, it's getting there. And then in the outer solar system, we have gas giants. And we really don't know about how life could start or exist in the gas giants. And, just the scale of the atmosphere of Jupiter is mind-boggling, right?
Yeah.
You can, is it 1,000 Earths you can hide inside the volume of Jupiter? It's an immense planet, immensely strong magnetic field, but, if you fell into Jupiter, there's hitting the surface doesn't really make sense. You fall through gas that becomes denser, that somehow becomes a bit of a liquid, etc. We don't really understand all of that.
Detail.
Yeah. It would be an interesting place to fall into. It would be a long way to fall. And of course, the core itself is thought to be this metallic hydrogen.
Yes,
Right? Ultra dense hydrogen where electrons can move freely, generate an intense magnetic field. So that's the solar system.
Right. Okay, so once we step out, that was all we had until 1995.
Right.
And now we've got, and so in particular, one of the things I find fascinating is until 1995, until we actually saw other planets, one of the major unknowns was that the way our solar system made its planets. is it the sort of thing that happens around any old star? In which case you're looking at one sort of processes that might happen. There's probably something that's going to happen while the star is forming and the leftovers get made into planets. Or is it something extremely rare, like, as actually was, at least in the distant past of astronomy, one of the most popular theories was two stars got close enough to each other that you've got to get really close and they rip off something. And so something came past the sun, ripped off a bunch of stuff that turned into the planets. And actually, that's extremely, if that happened, then we might be the only planets in the whole galaxy.
Yes.
But thankfully, into the mix comes observations, which is really great for science.
Yeah.
Really highly recommend observations if you're trying to do science. And now we know that they're all over the place. There's loads of planets.
There are lots of planets. So of course there have been quite famously this Kepler mission, and now there's the follow-up mission TESS. These are the experiment sounds simple, right? You look at stars and you look for the dimming of light as a planet moves in front. You need, really precise detectors and optics to do this at the level where you pick up planets. And of course, there are other methods that people have used, like the radial velocity thing, where you look for the wobble of a star as a planet goes around it. Okay. And essentially what we find is planets are relatively common.
Yes.
Right? So there are lots of planets. They're now, the ones that we know number into the 4,000 odd.
Yeah, it's a couple of thousand,
and that, taking into account the numbers we've looked at compared to the number of stars in the galaxy, that there are probably billions, or if not hundreds of billions of planets in the galaxy.
Yeah.
And of course, what everyone wants to know is how many are like Earth.
Yeah.
Right? Not really in any sense that we want to fly there and occupy. We just want to know what kind of environments are out there. And we do see in the news reports of another Earth-like planet discovered.
Yeah.
But you have to be very careful by what people mean when they say Earth-like.
Yeah.
I mean, you might think Earth-like is like the view we have here across the Adriatic, beautiful sea and mountains and olive trees, etc. Earth-like can be, it's got a mass roughly the same as the Earth, right? Or Earth-like, it's a distance from its star somewhat similar to the Earth.
Or it might have liquid water on its surface if there is any water on its surface.
Exactly.
It's an interesting one.
Exactly. So let's just play this kind of game of thinking about stars and planets.
Right.
Okay? So I'm going to start at the extreme end and start with the hot stars.
Sure.
Okay? Because really we're interested in life. What kind of environments can we have for life, right?
Sure.
If we think about planets around very hot stars which are the blue stars.
Yep.
Okay? Their energy emission is like ultraviolet and X-rays. Okay? So lots of energy coming off in high energy photons.
Sure.
Okay? That is not a good environment for life, right? Because the energies of those photons of light are enough to break apart molecules.
Yeah.
And you need molecules for life as we know it, complex life.
My favourite illustration of this, which I think I got off you. I think you put it in the book and I went, oh, that's interesting. A Fortunate Universe.
Yes, buy it now.
Yeah. It's the molecule in your eye by which we see, which has a bend in it, and then a light hits it, and it's just enough energy to straighten it out, and that's the trigger. That's seeing trigger. Now, if you don't put enough energy in your light, just microwave your eyes or something, it's a bad idea. But you won't see the microwaves because they might make this wobble, but that's about it. And with these sorts of stars, these lovely molecular bonds and molecular machines and molecular triggers, you just break it off.
Yes.
And so that's a bit of a disaster.
Yep. So I think those kind of environments are not good, but they're also rare.
Yeah, okay.
Okay, so that's fine. So, get down to stars, lower mass stars. And we think about a lot of the planets that have been discovered. And one of the big surprises has been the discovery of these basically very massive planets very close to stars.
Yes.
So these are stars, a star, and you have a planet, sort of the mass of Jupiter, but closer in than the orbit of Mercury. Yeah. And again, these are probably gas giant planets. Yeah. But they are very close to the star. They're being irradiated by immense amount of energy. They're massive enough to hold on to their gas. But again, that environment it's nowhere near the habitable zone, right? So there's no water, etc. It's lots of energy raining down on the planets. So those supermassive, the places where you have these big, massive super Jupiters, what are they called?
Hot Jupiters.
Hot Jupiters. They don't look like they're a place which is very good for life.
I've been reading recently, they also kind of ruin the rest of that star. So the best theory we have is you can't actually make them there.
Yes.
And so if you've got a hot Jupiter, the reason for that is the hot young star, once it fires up, whoosh, it can blow a whole lot of gas away. And so any star which is trying to bring in some gas to hold on is going to lose its supply. So you've got to get further away to make this hot Jupiter, and then it has to migrate in somehow. It's got to collect some stuff and some interactions with some things. And the thought is, if you've got something the size of Jupiter that just sort of wanders in through your planetary system until it gets closer than Mercury, it basically hoovers up everything along the way.
That's right. So I think there is still this outstanding question of why Jupiter didn't move in.
Yeah.
Maybe maybe the sun cleared out the solar system fast enough that Jupiter didn't have time to react and move inwards.
Yeah.
Maybe we were saved that way, but we don't know. This is still an unanswered question. Now, of course, we have to be very careful because hot Jupiters, those big planets near stars, they produce the biggest signal when you look at the Doppler motion. And also, if you've got a big planet passing in front of a star, it produces the biggest dips. So we have seen the things which are easiest to see, right? And as we know, in science, in astronomy, this is a selection effect. You see the easy things first.
Right.
And you have to be very careful about drawing conclusions for the entire sample based upon what was easy to see first. And these biases appear in all kinds of surveys that we do, and people argue over how you correct for the...
It'd be like trying to survey human beings by just finding the loudest ones.
Yes.
Asking them, and that's not going to be representative.
No. Okay, so we don't really know for most stars if they have solar systems similar to us. We are seeing that there are some stars out there that have multiple planets, right? So we're starting to see that there are groups of, a collection of planets moving around a star, and we're trying to understand what their environments are. But unlike the situation that we have in Star Trek, right? There is nothing fundamental to dictate what the surface gravity of a planet would be. Okay? In the sense that we already know it's 50 years since Neil Armstrong and Buzz Aldrin walked on the moon. And we know that on the moon, they experience a gravity 1/6 that of the Earth. When we watch movies of them on the moon's surface, right, they look a bit weird the way they're bouncing around. What we have to remember is that they're wearing a suit which on Earth would be very heavy, and if they tried to clunk around on Earth, it would be not very easy to do. But on the moon, where you've got this 1/6 gravity, you can bounce around, etc. Actually, do you know why they move the way they do?
Why do they have to?
Well, because the suit is pressurized. It's pressurized to such an extent that basically you're inside a rigid thing, right?
They can't. You can't leave that free because it'll just.
So you have restricted motion. You're inside a balloon. Right?
That's a good way to put it.
Okay. So the moon has a lower gravity than the Earth, but 1/6, that's quite a lot less, right? But there's nothing to stop at 1/6, right? 1/10, 1/50th, 100. You can go down.
What's the smallest thing we'd want to call a planet, though, right?
Well, in terms of gravity, it's the thing that if you jump, you don't get the escape velocity and leave, right?
It depends how high you can jump, I suppose.
Yeah. So, it's the Superman story, right? You eventually get to a planet small enough that you can leap and you can go right around the planet. Okay, isn't it part of the Superman issue? He doesn't have superpowers. It's just that
It's the sun, I thought, but it's the source of his in some mysterious way. But we've wandered off.
Yeah. Anyway, so the important point I want to make before I was rudely interrupted by myself.
By yourself. That happens a lot to you.
Is that we can also move upwards. Right?
Sure.
And it's not hard to imagine a planet with a surface gravity twice as much as the Earth. Right? Now, for us, that would actually be hard work, right? If imagine you're 80 kilos, you're suddenly 160 kilos, plonked along the surface, right? Your knees are going to suffer, etc. But why stop at 2, right? you can pack enough mass into enough radius to have a surface gravity of 10 times the Earth.
Sure.
Right? In that environment, you wouldn't survive. You would struggle to breathe. You'd struggle to inhale and raise your chest, etc. Similarly, why stop there? Now, those planets might be Earth-like in the sense that they might be in the habitable zone, might be able to have liquid water on the surface, but it'd be an environment which would be deadly for us. Mm-hmm. It might not be deadly to all life, right? Because you could imagine if a creature could evolve there, everything could have elephant-like bones to withstand the gravitational pull.
And the real easy way to do it is water. You just make whales.
Oh, yes. So we'll come to that in a moment.
Yeah. Sure, carry on.
Yeah. So your surface gravity of your planet could be immense, even if you have a rocky planet. Right. Which is it would be a very, very different kind of environment. The example you mentioned there with whales, I've said this before, and I'll say it again. One of the strange things about the Earth is that it has a surface which is 70% water and 30% land. Yeah. Right? Why do we have that mix? It would be much easier to have a planet that has no water. Yeah. Or a planet that has a lot of water. And it probably takes about twice the volume of water we have to basically cover everything on the Earth, and we'd have Kevin Costner water world. Right? And in the past, the Earth, in the Archean, when the Earth started up, it was thought to have a lot more water, and that there was essentially no dry land. Oh, okay. So we might be rare in that sense that there's probably out there a lot of very dry, bone-dry worlds, but potentially a lot of water worlds, because water is one of the most common molecules in the universe. Yeah. So there'll be water worlds out there. Again, you could probably swim in those oceans, right? You could, every time, if it's got a surface gravity 10 times that of the Earth, every time you lifted your head out of the water to take a breath, it would not be good. So there's a lot of variety there, and that's just in the habitable zone, right? You have planets towards the sun and further away; they could be frozen. Now, one of the examples that I've been looking at recently, which I found was very interesting. Another interesting thing about the solar system is that most of the planetary orbits are pretty circular. Yep. And the Earth's orbit is pretty circular. Yep. And people have been asking this question about what would happen if you have planets that are on more elliptical orbits. Yep. And you don't even have to leave the habitable zone. You could have the inner part of your orbit at the inner edge of the habitable zone, outer part of the outer part. Right. But you would have, it'd be
like seasons, but it wouldn't be because of the tilt of the Earth.
Right. And it would be much more extreme. Right. And if anybody wants an explanation for, winter is coming in Game of Thrones and why it's taken 8 years to get here. All right. Okay. It might be that kind of orbit. So you could have a situation where there are extreme seasons. And of course, if your orbit is big enough and you actually overlapped the habitable zone, you could have freezing cold environments out here, boiling hot environments in here. So elliptical orbits, we don't know. People are trying to study that now about what the equilibrium temperature is going to be. So the last one I want to mention is something to do with the most common stars in the universe. Mm-hmm. Red dwarfs. Yep. Okay, they're these little red stars. You create them anytime you create stars. For every star like the sun, you produce just a mass of these little red dwarfs. Right. And they're little and they're small and they burn forever because they basically.
Trillions of years.
Yeah, trillions of years. 75% of all stars are probably red dwarfs. Mm-hmm. And so you'd think that the majority of planets would be in the environment of red dwarfs. So maybe that might be the place where you'd expect to find life in the universe. Yeah. We already know that red dwarf stars are bad-tempered stars. They tend to flare and vary in brightness. Yeah. So one of the nice things about the sun is it's relatively stable. It has its hiccups. Red dwarf stars tend to be a bit flarier. But I read a really nice couple of papers recently on these objects known as eyeball planets. Ooh. Okay. So red dwarf star, smaller than the sun, fainter than the sun, means its habitable zone is smaller. Okay, quite close to the star. Yep. Take a planet, plonk it even in the habitable zone, and what happens is you get a tidal interaction between the planet and the star. Yep.
Now, what does that mean, a tidal interaction?
A tidal interaction. So, if the star and the planet were completely spherical, then the star would spin and the planet would spin, and they would just happily do their thing. Mm-hmm. But planets and stars aren't completely spherical. Our sun is very slightly squashed, okay? The Earth is slightly squashed,
Yep.
okay? So it's squashed into the poles, pushed out to the equator. And the Earth is also not a uniform density.
Yes.
It has variations in density. What that means is that as well as the pull from the sun on the Earth, there's these additional pulls on all of the sort of non-spherically bits.
Right.
The sticky outy bits and the high density bits.
Right. So it's sort of pulling the front a bit more than it's pulling the back.
Yes. And what actually happens is eventually that affects the rotation of the planet such that it becomes locked effectively in the lowest energy configuration.
Right.
This has happened to our moon.
Right.
The moon, the same face of the moon faces the Earth because of this tidal interaction.
Right.
Okay? And on the Earth, a lot of that tide, it also comes from the fact that we have water and that water changes shape,
Yeah.
pulls on the moon, etc. So you take a planet, a big planet, and you lock it towards the star. So one side is always facing the star, the other side is always facing away.
Right.
Even in the habitable zone, that is going to mean that for best case scenario, this side of the planet facing the star will be a hot, dry desert.
Yeah.
This side of the planet away from the star will be a frozen wasteland.
Yeah.
Okay, this could be an ocean here. But there would be a livable band
Right.
around
That's the best real estate.
That's the best real estate. But it's fragile real estate, right? Exactly where this band sits in terms of having liquid water and having life depends upon the brightness of the star, right? Because that can vary the habitable zone and change the region where you could have life on the planet. Nobody really understands exactly what all of these eyeball planets look like. I call it eyeball because you've got one side that distinctly looks like, an eye. It does suggest that even if we have planets in the vicinity of red dwarf stars, the chance of getting a planet whereby the conditions for life are ubiquitous all over the planet seem pretty rare.
All right. Okay.
Yeah. So, look, it's an unsolved question. The real distribution of planets is probably as big as our imaginations.
Yeah.
Right? But I think on the flip side, the chances of there being real twins of Earth out there, possibly quite rare.
So Geraint, we're still here. We're still at the foundations. No, that's not what it's called. Foundations of the philosophy of John Bell.
From the top.